This is class notes F in lesson 1. And the first thing I want you to notice about this class notes is that there is a star here. So you might be wondering, what are these stars about? So whenever I think a problem involves more complexity than normal or involves lots of different, concepts that you have to put together in sort of creative ways, I will put a star on it. So there's definitely something about this problem that makes it different, not so straightforward to solve. What could it be? And I alluded to this in the previous video. So that is that, first of all, this is a first order linear non-homogeneous ODE, okay? And if we were to try to solve this, right, we have a procedure. So this is the recap box of here. The first thing you do is you find the integrating factor. The integrating factor is antiderivative of a of t exponentiated. So you go up to the ODE itself, assuming again it's in standard form, and you look for a of t. Now here's the thing, right? So you might think for this ODE that we're going to solve, you might look at it very quickly and say, oh, this is a of t. So a of t is 1 over t. And that's not true, right? Why is that not true? Well, this is part of the reason this problem has a star. Because if we look at the standard form of the linear ODE, right, there it is up there, it is having a y prime by itself, right? So there's nothing that is multiplying y prime. That's not true in this ODE. So there's a 1 over t here. So in other words, when you go to find the integrating factor, even before that, the first thing you should do is you should check that the ODE is in standard form. Because all of the calculations we did a couple of class notes earlier to find this functional form from mu of t were from this standard form of the ODE, right? If it has anything other than a 1 in front of y prime, then this might not be the correct form for mu, okay? All right, so then what do we do to put this in standard form here? So first thing we do is multiply the entire ODE by t. All right, so I have dy over dt plus y equals t e to the t. Great, so at this point, we now have the ODE in standard form, and this makes it a little easier to identify the correct a of t. And we see that there's a hidden 1 here, and that is our a of t. So a of t equals 1. So that implies that the integrating factor, which is e to the antiderivative of a of t dt, is just e to the t. Again, I'm skipping the plus c here for the reasons I mentioned in the previous video. We just don't need it for this purpose that mu of t serves. So we have our mu of t, and again, I'm going to run through the different steps in solving these non-homogeneous ODEs to make sure that we have them, that we're comfortable with them. So the first thing is we multiply the ODE by mu. So here is the ODE. We're multiplying it by mu, so every term is going to acquire an e to the t. So e to the ty equals t e to the 2t, right? E to the t times e to the t is e to the 2t. And then the third step here is the left-hand side. If everything has gone correctly up until this point, the left-hand side should collapse into a product rule of mu times y. Again, I always like to check that. So the derivative of e to the t times y, product rule here, derivative of the first, derivative of e to the t is e to the t times the second, plus the first times the derivative of y, dy dt. And this does indeed match the left-hand side that we have. Great, so a little check mark there. So indeed, we've done our steps correct up until this point. So now we want to integrate both sides. So on the right-hand side, we are going to integrate t e to the 2t dt. Okay, so to do this integral, right, we are back to calculus. And how is that gonna work out? So integration techniques here. Let's talk a little bit about what they are. So we can't use u substitution here. That's not going to work. The only thing that might make sense as a u would be 2t. But that's basically going to give us some version of like u times e to the u or something, u over 2. And that's not going to help. So we can't do u substitution. So the next slightly more complicated technique than that is integration by parts, which I think is going to help in this setting. So how do we pick our u for integration by parts? So I'll give you a integration by parts. I'll give you a quick little mnemonic for this, right? So the mnemonic is I late for choosing u. And this basically means inverse, trig, logarithms, algebraic functions, trig, and then exponential functions. So this is a rule of thumb. So, this approach to choosing u in an integration by parts problem won't always work, but it's a good thing to try as a first step. The rule of thumb is choose u to be the function that first appears on this list from left to right. So, for example, in this particular problem, we have two types of functions. T is an algebraic function, right? These are powers and products and quotient and powers and products of T. So what about the second one? So e to the 2t. So this is an exponential function. So if we look at our list here, we have algebraic and we have exponential, and algebraic comes first, right? So we are going to choose u to be t in this example, and yeah, that's right. Sorry, I paused there because anyway, there's stuff going on in the environment that I had to quickly look through. Okay, so we're going to choose u to be our u equals t to be our you choose t to be our choice for u, and then dv is going to be everything else that's left over, which is e to the 2t dt. Great. So then we calculate here. So du equals dt, and then v is the antiderivative of e to the 2t, which is 1/2 e to the 2t. Again, I'm skipping the plus c's here. So we take all of this information and we put it into the integration by parts form. So that is u times v, so t times 1/2 e to the 2t minus the antiderivative of v du. So that's 1/2 e to the 2t times dt. Okay, great. So the first part of this is not being integrated, so that's done. And then again, we're integrating e to the 2t. So that brings out another factor of 1/2. So e to the 2t. And here I am going to put the plus c, right? Because we are now solving the first order linear ODE, which does have this arbitrary constant in it. So what do we get? We get t over 2 e to the 2t minus 1/4 e to the 2t plus c. And that is all going to be divided by e to the t to find our solution for y. So I get t over 2 minus, t over 2 e to the t minus 1/4 e to the t plus c over e to the t. Great. And then what am I going to do here? Well, these first two terms, they have an e to the t and they also have a 1/2. So I'm going to factor out a 1/2 e to the t. And what's left? 1 minus 1/2. Okay. Plus, t minus 1/2 plus c over e to the t. Great. So that is our standard, that is our final form here for the general solution. And then I want to go back and check whether there's an initial condition in this problem. And indeed there is. So y of 1 equals 1. Great. So I'm going to try to make some space here by erasing the integration by parts review here on the right hand side, and use that space to apply the initial condition. Okay, so the initial condition that we are asked to apply in this problem is y of 1 equals 1. So I'm going to go up here and start with the solution I just derived, which is over here, and I'm going to set 1 equal to y of 1. So everywhere I see a t, I'm going to plug in a 1. So e to the t becomes just e, and then t becomes 1. And then over here, we have a c over e to the first. Okay, so what's happening here? So, sorry, go back here. So 1 minus 1/2 is 1/2. Okay, times 1/2 is 1/4. So we have e over 4 is the first term here, plus c over e, and that's equal to 1. All right, and then I want to solve for c. So what am I going to do? So this is a little algebra exercise. So c over e plus e over 4 equals 1. So I'm going to subtract the e over 4 from both sides. C over e equals 1 minus e over 4. And then I'm going to multiply by e. So e times 1 minus e over 4. Okay. So that's my solution for c. It's not the most simplified version of c, but that's okay. Right? My job is just to figure out what c is for this ODE to find the solution to the initial value problem. So there I am, having figured this out. I'm going to plop it in here as the numerator to this final solution and box this as my final answer. Again, this took quite a little bit of work, and solving this for C is potentially tricky. And also, if we scroll up, right, we had this initial not issue, but we had this initial observation that the dy over dt term did not have just a 1 next to it. So again, that explains a little bit, gives you a preview, if you will, of why I put a star on some of these problems. You'll see this also in the practice problems. Let me just take a quick minute to show you where that is, to signal to you that some of these problems might be more involved than others. So I'm scrolling down here, and for modules 3 and 4, you'll see that some of these, like this problem right here, problem 17, does in fact have a star. So when you're trying to do a problem that has a star with it, if it's taking you longer to do it, or if it's a little trickier than the other problems, right, that is certainly part of the design of the problem. So this is the end of class note F.